In this example, our goal is to find the volume of a specific solid that is trapped between some planes and then the surface that we know as a paraboloid. And so far we know that in order to compute volume of a solid, what you want to do is set up a double integral over some region in the xy plane, and then you need to identify what function should be our integrand. And this function is telling us what is our upper limit that we're trapping our solid between. So this is going to be how the height of the solid is determined. So we need two things. We need to know what's R, what's our region of integration, and what's F. So let's get started. To get our region of integration, we know that we want to take a look at things that are we want to know how things are restricted in the xy plane. And so what we're going to do, while there's a lot of different functions going on here, we've got some planes, we got a paraboloid, we're just going to cut down our focus to only those equations that involve x and y. And we're going to worry about z later. So I am going to try to plot what my region looks like that's bounded in the xy plane so that I can identify what my region R is for my region of integration. So here's my xy plane, and I can draw my curves here. I'm told that x equals 0, so that's this line, is a bounding line, and then I've got y equals 1, so that gives me a horizontal line, and then I've got y equals x. Now I need to make sure that whatever region I select is actually bounded by the appropriate functions, because it kind of looks like, is this part down here somehow, like which triangle am I supposed to be picking? But notice I have to have x equals 0, y equals x, and y equals 1. And the only way to do that is to select this as my region of integration, R. Now, the rest of what's going on with my solid is determined by the space that is trapped between the plane z equals 0, which is just the xy plane, and the paraboloid that's sitting over it. So basically what I'm going to do is I'm going to try to draw this solid by first stretching my region of integration into a cylinder and then cutting it off according to how the top or the heights of my solid is supposed to be determined. So we can draw this 3D. And the way I should start is to plot my region R. And so this point that I've just plotted here is the point 1, 1. And the reason I chose that point is because I know it's one of the vertices of my region of integration. I know the origin is also a vertex, and then I know the point 0, 1 is a vertex. And so that gives me a way to get my region R translated into my 3D coordinate system. So here is R. Now I need to trap the volume that sits between this region and the paraboloid. And so I need to get a graph of my paraboloid on here. And this is a paraboloid that's opening in the positive z direction with its vertex here at the origin. The fact that there's a 3 in front of the y is just letting me know that it's changing sort of the skew of my paraboloid, rather than having cross sections at different z values look like perfect circles. They're going to look like ellipses. And so I'm just going to sketch, or try to sketch, just sort of a paraboloid that's opening in that direction, and then we'll go from there. So here's my paraboloid. Now, in order to figure out what my solid actually is, remember we said it's the space that's trapped between my region R, and the top stops at where you hit the paraboloid. And so to get this, I'm going to take my region and I'm going to stretch it into essentially a cylinder. And then I'm going to connect my points. And the space that I get here it's kind of like I've taken a triangular prism and scooped out part of it. And the solid that remains after I've removed that scoop is the solid that I want the volume of, and that's exactly this space. So we want to find the volume of this solid. So what I've added to my graph right here is just an example. This is like a sample. It's kind of like the 3D analog of a strip that you draw when you're integrating a region. So we know that when you take a region of integration, you are essentially you're integrating over little squares of that region, and for each of those squares is being when you transform that three-dimensionally, you are integrating essentially the volume of the prism that you get, the rectangular prism that you get, whose base sits in R and whose height is determined by the top of the solid, which in this case is that bounding paraboloid. And so our heights are determined by f of x, y equals x squared plus 3y squared, i.e. the paraboloid. So now we know what our f of x, y should be for the function we're integrating. So we can set up our double integral. And that function should be x squared plus 3y squared. But we also need to identify what our bounds are for our region of integration. And there are two considerations here. One, when you're setting up your order of integration, you want to think about, well, what's the function you're integrating? How difficult would it be to integrate your or to compute your antiderivatives? With respect to x versus with respect to y. Now this is a setup only problem. We're just setting up an integral, so that part doesn't so much matter here. But another consideration you need to make is how difficult it is to set up the region of integration or the bounds for the region of integration. For us, it doesn't matter if I put my strips in here as horizontal or vertical, because regardless, that whatever my orientation of my strip is, it's going to be determined on one side uniquely by a function and on another by a unique function as well. What I mean by that is, for example, if I put in my strips vertically, notice that I only have one bounding bottom function and one bounding top function. The same would be true if I put this in horizontally. I'd only have one left function and one right function. So I can get away with using just one double integral regardless of my order of integration. I'm going to go ahead and do dy dx so that we're handling the functions solved in the form y equals. And so the bottom function is the line y equals x, and so that becomes our bottom bound, x. And our top function is the line y equals 1, and so our top bound is just the constant 1. And then to determine our x bounds, we just want to identify what's the smallest x value in our region and what's the largest x value, because that's telling us where should we place all of our different strips so that we make sure we integrate over the whole region. And so that's between 0 and 1, since x ranges between 0 and 1. And now we have set up the volume of our solid. So we're done.